Hello and welcome to CMG's how-to videos regarding history matching in CMOST. As a good practice, we always recommend we QC all the data sources that we would like to load into CMOST and results. In this example, we have an IMEX simulation result file, SR3 file, along with the history matching information that we have from the field FHF files, and also the log files from two different wells. One of them is a PLT file for the producer number 1, and the other one is a pressure survey along producer number 2 at different dates. We also have the trajectory, so we can plot these log files along the actual well trajectories. So let's check the current level of history match that we have in the model. So we have two producers in the model, producer number 1 and producer number 2, and an injector. The producers are liquid controlled, so more or less the producers are matching the total liquids. Also producer number 2 is not even matching the primary constraints, but the injection also in this model is controlled by the pressure. So we have a constant injection pressure, and we're seeing a mismatch on the injection. If we move into the bottom hole pressures, obviously, as I said, the injector pressure is matching, but the wells, the producer bottom hole pressures are very much deviated from the historical measurements. The same trend we saw also in terms of the water cuts. As you can see, even the initial water breakthrough into the wells is not quite accurate. In the same way, if we move into the PLT plots, we have PLT from producer number 1, and this is the water cut around at 2015, and we can see very different water cut profiles for producer number 1, and we can check the same plot at different dates, and you can see even at 2017 we have highly mismatch values. And the same way we can check the pressure surveys for the producer number 1, producer number 2, and we see large differences in the pressures for especially for 2015 and 2017 when the well was in production with high rates. So now we are happy to move into the CMOST. So the first thing we need to load the CMOST application. I'm using 2020 mid-year release. So we can create a new project. So if you click on new project, we can call this new project as history match, and I can load my base data set, which I was plotting in results, and we can also create a CMOST folder. So we make sure all our files and CMOST related files are going to be stored in this specific folder. So if I say OK, that creates me a blank CMOST project. So each CMOST project can be made of several different studies. So I can create my first study, and that's going to be a history match study. So I can call this the first study again. Let's call it HM. And I can call my base data set, which is in this example will be the same as the project data set, but you can have different base data set for different studies. And the type of the study, I'm going to choose history match. So if I say OK, this creates me a blank new studies. We can go inside, double click and go inside. And this is a top to bottom workflow to complete. So if I choose general properties, you can see that the base data set is already loaded, and we also CMOST generated a new CMM file, which will come back to this. It's a master data set. It's called hm.cmm, and we can see the details of the SR3 that we loaded. So what I'm going to do here is to load the rest of the field measurements that we have, which includes of the FHF files. So load the FHF files that we have, and I can also load the log files. So they are also loaded into the current model folder. So I select both log files, and I have all the information required in this section. So I move into the next step under fundamental data. So CMOST is going to run hundreds, possibly thousands of simulations, and it's not practical or advisable to keep all the SR3 files. So what we're going to do is to ask CMOST to extract some specific information from any simulations that is complete, and then get rid of the actual SR3 file. So instead of maintaining gigabytes of the data for each simulation, we only keep small couple of kilobyte files, easy to read and easy to store, just specifically information that we need in this project. So I can ask CMOST for such a list. So the origin of the information that we're going to extract can be any of the usual data source that you have in results. Let's stick with wells in this example. So I'm interested in injection number, the wells, the injector wells, and let's start with bottom hole pressure. So I'm plotting the bottom hole pressure. Obviously it's matching the historical measurements because the producer was BHP controlled, but I can repeat the same plot for the two other producers that I have, so we can see the level of the mismatch. Okay, I can add another plot. Again, let's stick with the wells, and let's plot for example the liquid rates for the injection well. So liquid rate, which is in this case actually the water rate, is we have a bit of mismatch here. So we can repeat the same for the other two producers. And let's also add the for the producer, the water cut level. So water cut standard condition. And I can use again the repeat button to have the same plot for producer number 2. So that gives me an overall level of confidence that if in case in the later in the project I need any other data, I will have those information stored in the CMOST project. So we're skipping the user-defined time series for now. Let's go to the property versus distance. In results, we saw several pressure surveys and PLT plots. I'm going to include them in my CMOST project. So before anything, let's add the trajectory file also into CMOST. So that's stored under my current model folder. So load the WDB file. That contains all the trajectories for the all 3 wells. So if you say OK, now if I click on insert, CMOST automatically reads the log files, 2 log files, and extract all the profile plots that can be created based on those files. So if you click on the second option, I can pick and choose what I'm interested in. So I having the bottom hole rates and water cut, I can probably skip matching the oil rates. And so these were for the producer number 1, and for the producer number 2, we have the all 3 pressure surveys at different dates. So if you say OK, it can CMOST automatically plots the base data set based on our current data set against the log data that we have. And if you move to other plots, you can see the level of the mismatch between the history and the simulation current simulation model. Each of these property versus distance gets automatic names, but you can choose the names to more representatives if you're interested. Let's move into the next section in the CMOST, and that's parameterization. Here we have to define all the flexibilities that CMOST have in terms of changing the data set in order to get a match. So I can define those variables using cedit or a specific version of a customized version of Builder. So in this example, I'm going to use cedit. So click on the tab, and that's going to open the hm.cmm file that CMOST automatically generated. When we start, this is an exact copy of the base data set, that file that we loaded into CMOST. But I can now go ahead and define the variables within this master data set. So my that file already had some mod keywords. So if you are familiar with the CMOST with CMG datasets, these are the keywords that the range of the blocks, and they are defined under perm I. So they're going to change the permeability along these blocks, and in Builder already these mod blocks are defined based on the blocks around the well. So if I go ahead and parameterize multiplier, the first multiplier, which is 1 in this case, I can create a parameter, and I can name this parameter perm I mult prod 1. So you notice we have two blocks, one for blocks around producer number 1 and another block of mods around producer number 2. So if you say OK, the default value of 1 is going to be replaced with this variable name. Now I can copy the syntax and replace with the other multipliers for well number 1. So this ensures that whatever value is CMOST is going to assign for this variable is consistent around all the blocks around the wells. For the second well, I can similarly define a separate variable. So I want to treat these wells. They might have different damage zones, reduction in permeability. So if you select the default value number 1, I can create another parameter and call it, let's call it perm I mult prod 1. If you say OK, sorry, that's supposed to be a different variable, so I have to change this to prod number 2. Now if I select this, I can similarly go ahead and replace the values with this flag, which basically identified in CMOST as variable, or I can click on this location, hold the Alt card, and let's do something first. So we select the syntax and press Ctrl C. So we copy this syntax. Now go back and hold the Alt card and select number 1. You can drag the mouse and select all the values that you want to replace. And if you press Ctrl V, that's going to replace all the variables, all the values of 1 with the newly defined variable. The other change that we would like to make, or the variable that we would like to define, is under relative permeabilities. We have a bit of uncertainty on the relative permeability curves. The critical water saturation is currently set at 25%. I'm going to make this as a variable and define the variable. We're happy with the default name, and the current value set is 25%. So let's accept this definition. And the last change that I would like to make is the skin of one of the wells. So the skin in CMG is called is set under geometry keyword. So if you type in geometry, we have 3 geometries, one per well. So if you click on the first one, it corresponds to producer number 2, the one that I would like to actually parameterize. So select the value set 0, which is the default, and let's create a parameter. The name of the parameter can be, say, skin prod 2. So this is now represented by a flag, which tells CMOST this is a variable and has to be set. So if I save this, and I can possibly close, go back to CMOST. If you press import button now, we have 4 variables now in CMOST, and we can set different ranges for different variables. So if I start with critical water saturations, by default you can see it's a real value, can change to like something like discrete real, and set my own specific values if I would like to test 0.1, 0.2, whatever. You can set those values. But let's go back and stick with the continuous real. CMOST automatically takes the original value and goes 25% high, 25% low. So in this case, the range becomes 0.18 and 0.31. I'm happy with that. So for permeability reduction around producer number 1, let's provide a value like 0.1 to 1. And for the producer number 2, let's stick with the same range, so 0.1 and 1. And for the skin, let's set a value between 0 to, say, 5. Okay, so if we save, that's going to be the variables that I'm allowing CMOST to play with. The next step is to set the objective function. So for history match, we have a dedicated tool that looks at the elements of the history match. So this can be made of different local history match errors. So if we insert the first one, I can create the first history match error based on the producer number 1, and let's call it history. Now at the bottom, I can set elements that are attached to this local term. So they can be original time series, user-defined time series, or property versus distance. So I'm going to add the first. This is going to be based on the time series. So you can attach different. The origin can be from, again, any of the usual sources in data sources. Let's stick with wells. And for the producer number 1, I'd like to match liquid rate. And let's also add for producer number 1, I'd like to match water cut, and I'd like to match also for the producer number 1, the bottom hole pressure, well, bottom hole pressure. Now let's create the same element for producer number 2 as well, or I can dump all the same time series for the producer number 2, but I'd like to have them separately and have more details in my experiment table when my simulations are run. So let's create another local term, and let's call this prod2 and hist. So similarly, I'm going to add for the producer number 2, I'm going to try to match liquid rate, let's add the producer number 2, and that's going to be my water cut, standard condition, and let's also match for the producer number 2 the well bottom hole pressure. Okay, so I have two sorry, for producer number 2 it has to be well bottom hole pressure. So we have two elements for matching the history for these producers. I can also now add another term for tracking the error on producer number 1. Producer 1, that's going to be PLT. So let's add the errors on PLT 1. So remember that we have these plots for producer number 1, PLTs, bottom hole rates, and water cuts. So I can now, instead of using the original time series, we're going to use the third tab, properties versus distance. And I can add my first property versus distance that I'm matching. So from this list, we have the 7 property versus distance plots that we have. We already had them in the fundamental data. I'm going to use the first one, which represents, if I go back, it's bottom hole for this well at 2 different dates, 2015 and 2017, and the other 3 are again correspond to producer number 1. So let's add the first 4 into this term. So property business number 2, I want number 3, and I'd like number 4. So that tracks the error that I have on PLT. Let's add another independent term to track the well survey error on well pressure surveys. So and that's going to be on prod 2 well pressure. And those are captured by the remaining 3, the last 3 pressures, property versus distance plot. So 5, 6, 7. So again, these are 5. So well pressure at 2017, 2015, and 2012 for producer number 2. Okay, so that's going to be my history match error for this term. Now all we need to complete is to set the control setting. So if I go to engine setting, we have different engines to run history match. Let's stick with the default CMG DCE. I can set how many I have. If I have different history match, global history match functions. I can choose the one that is relevant, or I'd like to set my history match based on. So in this case we have only one, and obviously we're going to minimize that. We can set the maximum number of experiments that I would like to run. So let's assume we're happy to run 150. That sets my engine setting. The next step to define where we would like to run those experiments. So we have the cloud option, which you can use in terms of as a pay-as-you-go. It's a separate service. You need to contact us to get subscription for this cloud service. But if you're running locally, you can choose the scheduler. Please make sure the CMG scheduler is already CMG launcher is up and running, so you have access to the local scheduler. You can refresh if that wasn't active, which probably means that the launcher is not accepting jobs. You can choose the version of obviously the simulator is going to be IMEX, and you can choose the version of IMEX that you're running. I'm running the latest version currently is 2020.23. You can set how many CPUs you're happy to use per job. Let's say I'm happy to use 4, and you have the options to avoid wasting simulation time if the runtime is more than say, I don't know, 0.5 hours, half an hour. Then simulation can stop, so you're not wasting time for some random numerical convergence problems. The next important bit here is to set how many concurrent jobs that you like to run. So if you have enough CPUs, you can run multiple jobs on the machine, obviously. The other limiting factor is going to be licenses. The good news is that CMOST comes with a 4 times multiplier for IMEX and 2 times for gem and stars. So with one single IMEX license, you can run 4 concurrent simulation without needing any additional licenses. So let's say we're happy to run 4. That's the end of the setting up stage. So all you need to do is to go to top and start the engine. So that's going to check all the settings, double checks the running scheme. So if you say OK, now if CMOST starts processing. So if I go back to control center, you can see that what CMOST currently is doing. So created initial experiments. So I can go to my experiment table, and I can see the initial set of experiments CMOST has created. So currently 16 new experiments have been created, and you can see the values CMOST is testing for in each experiment. As simulation continues, this is going to be, the table is going to be completed. So once the simulation, the first simulation is finished, we'll have the individual error functions from each data set. So we can go to launcher, and if I refresh, I can see the 4 jobs that are actually running in CMOST now. CMOST passes those runs to launcher, and we can see that how we're progressing.